Now, all of these stuff, the previous stuff like this, time of action and other observations, the change in the momentum of the different bodies for same interval of the time is caused by the same amount of force. And another concept here, the direction of the momentum change is given by the applied force. Combining all these, combining all above observations, we get what? Second law of motion, given by whom? Newton. Okay, that's also called Newton's second law of motion. So Newton's second law of motion is actually the outcome of all the observations which I discussed earlier, the change in the momentum and the relaxation time given in the action of the change in the momentum. So for that, Newton said that he gave a law called as Newton's second law, which says that, now keep that in mind, the rate of change of momentum. Change of momentum is important, okay? It is not the momentum only. There must be a rate of change, that is the change in the momentum with respect to time. If a body is made to change its momentum for a longer period of time, that means the force applied to it will be smaller. And if there is an instant change, for example, I will show you diagrammatically here. Suppose this is a momentum axis and this is a time axis. With respect to time, say for example a body is having this much of momentum for some time of period, and here force is applied. At this point of time, force is applied. There will be few conditions. If there will be time of action or relaxation time will be very much higher, that means the change in the momentum will be there from this point to downwards, but the time of action will be more. So that means lesser the force will be have been applied here, because the time of action is very much high. If more force is applied, that means the change in the momentum will happen in lesser amount of time. And if there is an almost instant change, that is momentum change from P to 0 instantly, so that means the force applied is high. Okay, higher force is applied in this case, and in that case lesser force is applied. Okay, because here the relaxation time is given very much higher, and here instantly the body is instantly stopped. That means force is applied at a time, huge amount of force is applied. So that means the change in the momentum is dependent upon the relaxation time, also the time of action. Okay, now the second law of motion says that the rate of change of momentum, the rate of change of momentum of a body is directly proportional. That means more the one quantity, more will be the another quantity upon which it is dependent. Okay, lesser the quantity 1, lesser will be the second quantity upon which it is dependent. Okay, so momentum of a body is directly proportional to the applied force, which I have talked earlier, applied force. And second thing is that the change, that is the change in the momentum, change takes place in the direction, in what direction? I have told you, the change in the momentum takes place in the direction of the force applied. Okay, so the change takes place in the direction in the direction in which the force acts. This is important. That is, the change in the direction of the momentum is determined by the force acting over onto the body, and the rate of the change of momentum is directly proportional to the applied force. How that can be mathematically determined? We can write it down mathematically as follows. So mathematically we can represent this by, so for that we have to fix it first, that what change does mean. So for that, suppose I have I'm acting a force is applied on a body with mass m, Suppose this is the body with mass m and force is applied onto. There will be a change in the momentum. And the direction of the change in the momentum will be as that of the direction of the force. Here in this case it will be along this axis. So suppose I am representing force is applied. Force F, represented by F, denoted by F, is applied on a body with mass m in time interval delta t. This is the change in the time of, that is the time of action. This is the time of action. Okay, so time of action is delta t and the force applied is F on a body m. So if this body possesses the momentum, at first it possesses p momentum, and then momentum gets changed or increased or decreased, that depends upon the situation. Here in this case momentum increases from p to p plus delta p. Delta is representing the change. So change in the momentum is this much. Okay, so momentum changes from p to p plus dp. So that means change in the momentum is what? Delta p. So that means momentum is changing from p to p plus delta p. This is the change in the momentum. Now what does second law says? How it can be written mathematically? Mathematically, second law of motion is as follows. Okay, now see, we have said that the change in the momentum is directly proportional to that of the force applied onto the body. So that means force will be directly proportional to rate of change of momentum with respect to time. Change of the momentum, I have to write down it, rate of the change of momentum. Okay, that is the rate means with respect to the time. So rate of change of momentum, that is with respect to time, this gives the force applied on a body. Okay, or we can say it implies F will be equal to, if proportionality is taken by the constant, that is the constant of proportionality, and here in this case from the experimentations it has been observed that there isn't any role of this very constant here, so this is taken to be as unit constant. Okay, so its value is equal to 1. Keep that in mind, k is equal to 1. So F will be then equal to, F will be equal to k multiplied by delta p by delta t, or we can say F will be equal to, K is equal to 1, so F will be equal to delta P by delta T. This is for longer, bigger changes. Suppose time of action is very much small, is very, very small, is very, very small. That means delta T is approaching to 0. That is, instantly the force is applied. For example, here I'm applying force. There is an instant displacement inside the object. So that means force is applied instantaneously, okay? Because in classical mechanics, instantaneous effects are observed in principle of classical mechanics, not in the quantum and higher advanced physics. So here, we suppose that the time of action of the force is instantaneous. So for that, further, we know that if delta y by delta x, this is a mathematical perspective, supposing that the limit is applied upon the delta x tending to 0, that's the limit actually. You might be observing this very thing in mathematics, the differential equations, also in differentiability stuff. So for that, limit delta x tending to 0, delta y by delta x, this is equal to, is written as dy by dx. Keep this very thing in mind. This is called as the differential coefficient of y with respect to x. So in this case, if f is equal to limit delta t tending to 0, delta p by delta t, this situation arises. That means the time of action is very, very much small. It's instant action. So in that case, the f will be written as, this delta will be replaced by the differential coefficient. And what does that mean? Here, in that case, f will be written as, I'll write it down first, limit delta x tending to 0, sorry, delta t here, this is the time, delta p by delta t, it will be written as, this will be changed and replaced by the differential coefficient dt of p. So which means that f will be equal to the rate of change of momentum with respect to time, and the time of action here is very, very smaller. So this is the this is what this statement of mathematical statement of second law. What did that say? That the force applied onto a body is equal to the rate of change of momentum with respect to time. Furthermore, we can derive from this very statement F is equal to, we know that momentum from the first definition, we have said that I am solving this very these very mathematical equations in scalar form, okay? Although these are vector as well, these are the vector quantities, but I am supposing that the action is taking place in one direction only. Action in one direction. So that is the reason I am taking these scalars. Otherwise, these are vector quantities. Keep that also in mind. I will deal with that very stuff further later on. We know that momentum is equal to the product of mass and velocity. Put it here. So d by dt of p. P will be now p is equal to m into v. Okay, now we have supposed that the mass of the object is m and we are applying a force and it will be displaced or whatever happens to this very body, but the mass remains constant. So mass is constant. We are not destroying the mass, we are not changing this very body into some another body with different mass, because it will be the same as that of the initial state. So mass will be constant. What changes only is velocity. For example, here the velocity is 0 and the momentum is changed from this very position to this very position. Upon changing this, we are getting a change in the momentum. Say velocity changes to v. Okay, so there will be a change in the velocity from 0 meters per second to v meters per second, say 10 meters, 20 meters, whatever that is. So the only changing term here is the velocity. So we can write it down as m is constant, keep that outside. The only differential coefficient will act only upon the velocity term here, so it will be represented by dv by dt. And we know this term, it is the acceleration. Simple. Acceleration is equal to the rate of change of velocity with respect to time. So that means force will be equal to the product of mass and acceleration. This is another form of second law of motion. So that means second law of motion, another statement says that force is directly proportional, or we can say simply proportional to the product of what? Mass and acceleration which it possesses at that time, at that instant of time. So product of mass and acceleration actually gives the body's force applied onto that. So if at any instant we apply some force, we will get ultimately the acceleration caused by that force. And that force, from this we can derive the acceleration. The acceleration of the body at any instant when the force is applied is given to be equal to force divided by mass. Okay? This is the acceleration caused by that very force at any instant of time. Now, here